We often take the world around us for granted. We rarely stop to ponder the forces that govern the everyday phenomena we observe. Yet, hidden in plain sight are fascinating processes shaping our world. One such process is natural convection, a silent mover that plays a crucial role in countless natural and engineered systems. Natural convection is the process of heat transfer driven by density differences. Warmer fluids become less dense and rise, while cooler, denser fluids sink. This continuous cycle creates fluid motion, transferring heat without the need for external forces like pumps or fans. It's a fundamental principle that governs everything from atmospheric circulation and ocean currents to the cooling of electronic devices and the design of energy-efficient buildings. In the realm of engineering, understanding natural convection is paramount. It influences the performance and efficiency of a wide range of systems, including heat exchangers, cooling systems for electronics, and even nuclear reactors. By harnessing its power, engineers can design more efficient and sustainable technologies. Imagine a hot cup of coffee left to cool on a table. The heat from the coffee is transferred to the surrounding air, causing the air near the cup to warm up. This warmed air, now less dense, rises and is replaced by cooler air from the surroundings. This cycle of rising warm air and descending cool air is natural convection in action, a silent dance of heat and fluid flow. On a larger scale, natural convection is responsible for atmospheric convection patterns, which influence weather and climate. In the oceans, convection currents play a vital role in distributing nutrients and supporting marine life. Architects and engineers leverage natural convection to design buildings that are not only energy efficient but also comfortable for occupants. Passive cooling systems, which rely on natural convection, reduce the need for mechanical cooling, thus saving energy and reducing carbon footprints. From the simple act of boiling water to the complex dynamics of weather systems, natural convection is a fundamental process that impacts our daily lives. As technology advances, understanding and harnessing natural convection becomes increasingly important for developing sustainable solutions. Future innovations in energy, climate control, and environmental management will likely depend on our ability to effectively utilize natural convection. Observing natural convection in nature can inspire new ways to solve engineering challenges, leading to more efficient and eco-friendly designs. So the next time you feel a breeze or watch steam rise from a cup of coffee, remember the invisible forces at play. Natural convection is a powerful yet often overlooked phenomenon that shapes our world in profound ways. Natural convection is all about density differences, but why do these differences matter? The answer lies in the concept of buoyancy. Imagine a helium balloon. It floats because helium is less dense than air. Similarly, in a fluid like air or water, less dense portions experience an upward buoyant force causing them to rise. Temperature plays a crucial role in density variations. As a fluid heats up, its molecules move faster and spread out, decreasing its density. This heated, less dense fluid becomes buoyant and rises. Conversely, cooler, denser fluid sinks, creating a continuous flow. This density-driven flow, fueled by temperature differences, is the essence of natural convection. It's a delicate balance between buoyancy forces, gravity, and fluid viscosity. Understanding how these forces interact is key to predicting and controlling natural convection in various applications. Consider a radiator heating a room. The radiator heats the surrounding air, making it less dense. This warm air rises towards the ceiling, creating a convection current. Cooler air from other parts of the room is drawn towards the radiator, creating a continuous circulation that distributes heat throughout the space. To effectively analyze and predict natural convection, engineers rely on a set of dimensionless numbers that characterize the flow behavior. These numbers are essential in simplifying complex fluid dynamics problems, making them more manageable and understandable. These numbers, like secret codes, unlock valuable insights into the complex interplay of forces at play. They help engineers decode the mysteries of fluid behavior, providing a clearer picture of how different forces interact. The Grashof number quantifies the relative strength of buoyancy forces to viscous forces. It is a crucial parameter in determining the nature of the flow, especially in systems where temperature differences drive the movement of fluid. It tells us how dominant buoyancy-driven flow is compared to the resistance offered by the fluid's viscosity. In other words, it helps us understand whether the fluid will flow freely or if it will be hindered by its own internal friction. A higher Grashof number indicates stronger natural convection. This means that the buoyancy forces are significantly overpowering the viscous forces, leading to more vigorous fluid movement. The Rayleigh number, a product of the Grashof and Prandtl numbers, provides a comprehensive measure of the flow regime. It combines the effects of buoyancy, viscosity, and thermal diffusivity into a single parameter. It helps determine whether the flow is laminar, smooth and orderly, or turbulent, chaotic, and unpredictable. This distinction is vital for engineers as it affects heat transfer rates and overall system efficiency. A critical Rayleigh number often marks the transition between these regimes. Understanding this transition point is crucial for designing systems that either avoid or exploit turbulent flow. The Prandtl number characterizes the fluid's properties. It is a dimensionless number that provides insight into the relative thickness of the momentum and thermal boundary layers. It represents the ratio of momentum diffusivity to thermal diffusivity, indicating how effectively the fluid transports heat versus momentum. A high Prandtl number means the fluid has a thicker thermal boundary layer compared to its momentum boundary layer. These dimensionless numbers are powerful tools for engineers. They simplify the analysis of complex systems by reducing the number of variables and highlighting the most critical factors. By calculating and analyzing them, we can predict flow patterns, heat transfer rates, and the overall behavior of natural convection systems. This predictive capability is essential for designing efficient and effective thermal management systems. They provide a common language to understand and compare natural convection phenomena across different scales and fluid properties. This universality makes them indispensable in both research and practical applications. Think of these numbers as the ingredients in a recipe. Just as the right combination of ingredients determines the success of a dish, the correct application of these dimensionless numbers ensures the accuracy of fluid dynamics predictions. The Grashof number tells you how much flour to use, indicating the strength of buoyancy forces in your system. The Prandtl number dictates the amount of sugar, representing the balance between momentum and thermal diffusivity, and the Rayleigh number reveals the final texture of the cake, showing whether the flow will be smooth or turbulent. By understanding these ratios, we can predict and control the outcome of natural convection processes. This knowledge allows engineers to design more efficient systems, optimize performance, and innovate new solutions in the field of fluid dynamics. Section 4. From gentle breezes to raging storms, predicting flow behavior. In this section, we delve into the fascinating world of fluid dynamics, exploring how we can predict the behavior of fluid flows under various conditions. In the world of fluids, there exists a delicate balance between order and chaos. This balance is crucial in determining how fluids move and interact with their surroundings. Natural convection, driven by buoyancy forces, can manifest as smooth, predictable flows or transition into turbulent, chaotic regimes. This phenomenon is observed in various natural and industrial processes. The key to predicting this behavior lies in the Rayleigh number. This dimensionless number helps us understand the conditions under which fluid flow will remain stable or become turbulent. For low Rayleigh numbers, viscous forces dominate, keeping the fluid motion ordered and stable. In such scenarios, the fluid moves in a smooth, layered manner with minimal mixing between the layers. This laminar flow regime is characterized by smooth, predictable streamlines resembling layers of fluid gliding over each other with minimal mixing. This type of flow is often seen in slow-moving fluids or in highly controlled environments. As the Rayleigh number increases, buoyancy forces gain prominence. These forces cause the fluid to become more buoyant, leading to increased movement and mixing within the fluid. The flow becomes unstable, transitioning from laminar to turbulent. This transition is marked by the appearance of eddies and swirls, which disrupt the smooth flow of the fluid. This transition point, often associated with a critical Rayleigh number, marks a dramatic shift in flow behavior. At this critical value, the fluid flow changes from being orderly and predictable to chaotic and complex. Turbulent natural convection is characterized by chaotic eddies and swirls, resulting in enhanced mixing and heat transfer. This type of flow is common in many natural and industrial processes, where efficient mixing and heat transfer are essential. While more complex to model, understanding turbulent natural convection is crucial in many applications where efficient heat dissipation is critical. Industries such as power generation, HVAC, and electronics rely on accurate models to ensure optimal performance and safety. Imagine a calm lake on a windless day. This represents laminar flow. The water is still and undisturbed with minimal mixing and movement. Now visualize a raging storm with waves crashing and swirling. This is akin to turbulent flow. The water is in constant motion, with chaotic eddies and swirls creating a complex and dynamic environment. The Rayleigh number helps us predict when natural convection transitions from the peaceful lake to the turbulent storm. By understanding this concept, we can better anticipate and manage the behavior of fluid flows in various applications, ensuring efficiency and safety in our designs and processes. Section 5. The Edge of Change. Modeling boundary layers accurately. In the realm of fluid dynamics, the region where a fluid meets a solid surface is a zone of significant interest and complexity. This region, known as the boundary layer, plays a crucial role in natural convection, influencing both flow patterns and heat transfer rates. Within the boundary layer, the fluid velocity varies significantly from zero at the surface to the free stream velocity away from the surface. This velocity gradient creates shear stresses that influence the flow behavior. Simultaneously, heat transfer near the surface is dominated by conduction due to the reduced fluid motion. Accurate modeling of boundary layers is essential for capturing the overall behavior of natural convection. A fine mesh near the surface is crucial to resolve the steep velocity and temperature gradients within the boundary layer. Consider a spoon dipped in hot soup. The layer of soup clinging to the spoon's surface represents the boundary layer. This layer heats up faster than the surrounding soup due to conduction. Accurately modeling this thin layer is vital for predicting the overall heat transfer from the soup to the spoon.